I had some comments on batch norm, and this is an important architectural element. And in my head, I had noted it under regularization and not under architecture, but I can add it to architecture, and it really, and thanks for pointing that out to Peter, that really addresses the question you raised. Yeah? And I think I failed to connect the dots in my head in the moment you asked. So in batch norm, what we do is we, well, as the name implies, we normalize across a batch. So if we have, this is now the ith training example, so this is a vector. And from this vector here, I now consider the jth component. And from this jth component, we can subtract the mean as computed from this particular batch B. So a batch is just a tiny subset of training examples. And well, this would be subtract mean, and then there's also standardize. So divide by sigma j, also computed from this batch, squared. So this would be the variance computed from this batch, and here a small number larger than 0 to help regularize, to prevent division by 0 if at some point there's, this estimate here were 0. And this gives me a new feature xi. Let me write twiddle. I also put the dependency on the batch here. And this is again the jth element of it. And now there's an extra set of learnable parameters, namely, and that then produces my final output. So my output from this batch norm layer would be z, a vector. For the ith training example, we're looking at component j here. And now we have two trainable parameters. This would be gamma j times this x tilde I b plus beta j. And probably I should also put the batch here. And these are now learnable parameters that do not depend on the batch. They're independent of the particular batch. And then at test time, so this would be at train time, and at inference time, a batch norm layer will output or will use this kind of transformation. And the problem is that at inference, we don't really have batches. Well, okay, maybe you do, but maybe you don't. If you don't have batches, then you can use a running mean to estimate these here means and variances. Okay. And so this is very widely used these days. And the work on why it works so well, I would say, is still ongoing. So one argument goes that it reduces internal covariate shift. What this means is that it reduces the impact of changes in previous layers. Because when we use automated differentiation to update the weights in our neural network, we change also the earlier layers, and that will change the input to a particular layer. And sometimes the changes can be too drastic if the learning rate is too high in particular. And so this helps cope with larger learning rates. And these larger learning rates, on the one hand, they can just speed up the training, and on the other hand, they can also help you get out of local minima. And it helps avoid vanishing or exploding gradients. Good. Now, batch normalization is not the only kind of normalization out there. So in convolutional neural networks in particular, these perceptrons are within the layers, they are arranged by channels, and then one can also normalize across channels, or one can normalize across parts of different dimensions. This would be something called a group norm layer. So basically all permutations of what you can locally average over have been published and result in a different kind of normalization layer. And that is okay. And we have this added source of randomness here, because these parameters that we estimate, they depend on the particular batch. And so this is offered as one explanation of why this is also considered as a regularizer. So very hand-waving, I'm sorry. But I think it reflects the still limited understanding of what they do. And this has historically been the successor of dropout. So before the batch norm, dropout was widely used, where at train time subsets of neurons are omitted or killed. And then the argument was also that through this added source of randomness, regularization would take place. And on the other hand, another interpretation was that effectively we train an ensemble of neural networks in that way, but batch norm works better. And yeah, so Peter gave this example. If I want to, let's say if my input numbers are really tiny, 10 to the minus something, and I want to perhaps solve a regression problem, I want to get out fairly large numbers, then this kind of normalization will be really helpful. Good. So much for the first footnote. Almost 2 hours into the lecture. Let's talk about the kinds of losses briefly. So very briefly, for regression, the standard loss to use is L2, or maybe you want to use some kind of robust L2 if you have outliers, Huber loss or so. And for classification, typical loss would be to use cross entropy. But there are many others. Yeah, notably, if you work with images, and if you have a sparse foreground class, so if it's more important to get the foreground just right, or let's say you work in medical physics and you want to segment out the tumor just right, then you're much more interested in the foreground class. Then you can do things like use things like the dice loss, or there are okay, so let me say for imbalance problems where you care more about getting one class right than the other, you can do things like dice, or there's something like the focal loss, and many others. So in the image domain particularly, a huge number of loss functions have been studied, and the Meyer-Heinz from DKFZ here, they have produced a really nice survey article enumerating all these kinds of losses and which one is appropriate to use in what case. Okay, but I want to jump to 3, the regularization. Now, the regularization on parameters that we can apply to our weights in the neural network. Maybe the most popular choice is to use an L2 loss or weight decay. So L2 loss, as the name implies, we just add to our loss function the norm of our parameter vector squared. Weight decay has the same effect, but this is more in the context of gradient descent, where when we update our weight vector, we make it a little bit smaller at every time step. That corresponds to implementing an L2 loss. And as we have seen in ridge regression, this leads to less extreme parameter values. Yeah, so it makes somehow for a more stable neural network. It helps prevent overfitting. There's also the L1 loss, which we know from the lasso, which induces sparsity. So this can give me weights which are exactly 0. And if that helps reduce computational footprint or not depends on the architecture. In things like GPUs, so if we use standard multi-layer perceptron of this regular shape, or we have the same number of perceptrons in each layer, this is going to be implemented in using matrix multiplications. And if one of these perceptrons has 0 weights, a GPU cannot effectively use this kind of sparsity. But other architectures, so if you do compute on a more CPU-like architecture, that can be useful. Yeah, so that's when you would use the L1 loss. And then there is a combination. So L1 plus L2 would be called the elastic net. And let's look again at this ball, the unit ball for the L1 loss and the L2 loss. So this would be the unit ball for the L1 loss. This would be the unit ball for the L2 loss. And we saw that this L1 loss has this property of attracting, you remember the kind of pictures that we had drawn, like we have a posterior probability of what could be my regression parameter. And then we saw that as we regularize more and more, we have this path of solutions, which under L1 regularization, would look something like so. And I should have drawn an isotropic example. Let me try this again. So for some given regularization strength, I can distinguish two different cases. If my isotropic posterior distribution lies maybe here, then if I use this particular constraint, my solution is going to be this one. So it's not going to be sparse, because I'm going to use my feature number 1 and I'm going to use my feature number 2, not sparse. But if, on the other hand, my posterior would have been here, I would have created a sparse solution. Yeah, I'm using only this feature but not the other one, because I'm here intersecting with the constraint. Yeah? And I'm only using, these were the axes, beta 1 and beta 2 we wrote at the time. I'm only using beta 2. Now, if you think about where does this transition happen, about sparse solution or not, for a given strength of the constraint, it happens exactly in this cone that I have tried to show here. Yeah, so there is this cone. Let me call it the cone of sparsity, or the cone of sparse solutions, that's associated with this L1 loss. So this is the cone of sparse solutions, and this cone assumes that our posterior here is an isotropic distribution. All right, and if I now add up the L1 and the L2 loss, I obtain something which does have a kink here, but which is round in between. So I have a, I have a small cusp here. This would be the elastic net here, yeah, which is L1 plus L2. So I'm really using the L1 norm of my parameter, and I'm using, let's say, lambda 1 plus lambda 2, the L2 norm of my parameter vector. And now this cone, where I obtain sparse solutions, this cone where I obtain sparse solutions, it now shrinks, it becomes narrower. Okay. This is my new cone of sparse solutions. And so on. So this elastic net is still sparsity inducing, but less so than the pure L1 norm. And it has some of this nice stabilizing effect of the L2 loss. So this is also quite popular as a regularizing side loss. Okay, now this was if we regularize the parameters, but instead I can also regularize so still footnote 3. I can regularize the output itself. I was writing O for output here. And a common solution is to use entropy regularization. In the context of classification. So when we have this one hot vector F of possible outputs, we just use a side penalty, which is the entropy of this. Yeah? So I have an index here for the classes. So my ith training sample, the kth class. And this helps reduce the overfitting and improves generalization. So it makes the network, you force the network to become a little bit less confident in the predictions that it makes. And it's a really, simple trick to use. And Pereira and godfather of neural networks and Nobel Prize winner Hinton have shown this in 2017. And by the way, going through my lecture notes and papers and so on, I mean, Hinton is in so many places. It's just amazing. Benjo also, to be fair, Le Cun also. But Hopfield, not really. So interesting that, yeah, he got part of the prize. Good. So this much about the loss function. Then the training data. Now, obviously, you need maybe I will add one more. Obviously, you need training data that well represents what you're going to see later in life at test time. And usually, you would like to have more training data than you do. And in such situations, Münchhausen style, you try and pull yourself out of the mud. And machine learners do this by using the training examples that they have and then manipulating them to produce more artificial training examples. So, for example, in, let's say, an image classification, you would use, let's say you have some image, xi, and then you have the label. What you could do is, in data augmentation, that you take the same image and you make it a little bit larger, or you make it a little bit brighter, or you add a little bit of noise, and you add again a little bit of noise, or you even obscure parts of the image, or if you want to, now all of the things that I've said, they work well for detector images. If you work with natural images, then if you want to recognize objects, you could say, okay, I'm zooming in a little bit, or I'm shifting my object a little bit around. So all of this creates you extra images. So it's data augmentation. There are even crazier augmentations, like mix-up, where you just take training examples from different classes. So let's say in images, yeah, you take an image from one category and you take an image from another category and you interpolate linearly between the images. And these interpolated images, they look nothing like reasonable images. Yeah, it's like, you're drunk and you're looking at a superposition of two images that have nothing to do with each other. And then you interpolate the labels accordingly, and strangely this helps. Or if you work with geometric objects, then you may want to take the same object and, Peter is working a lot with point clouds. You can take a point cloud and its class, and then you can rotate that point cloud, and it will still belong to the same class. Yeah, that would be one reasonable way of augmenting your data. And Peter, could you stop the recording for a moment, please? Thank you. Bring it back on. Good. We can still say a few things about optimization. In optimization, the standard approach is to use some form of gradient descent. So we have a parameter vector that is now at iteration t. And we say that we start from our estimate at iteration t minus 1. And then we compute the derivative of our loss with respect to the parameter vector. And here we use the parameter vector from time t. And this would be plain gradient descent. And naively, it looks like that would be, if you have enough computational resources, it would look like that's the thing to do. But it turns out that it's even better if you only use a small number of training examples at a time. So you do not compute your loss from all training examples, but only from a batch, a small subset. And that gives you stochastic gradient descent, or SGD for short. Well, and why is that important? Because it really helps you escape. So empirically, what we see, that it helps escape local minima. And it speeds up things incidentally, and it also, it turns out, regularizes. So it's a win-win-win. You know, one of these rare situations in life where it's not really a trade-off. It's just better in all directions. And the one thing you need to optimize when you say, I want to do stochastic gradient descent, is to decide, you know, how big is your batch going to be. And well, if we try and understand what it does, now really I would have to draw high-dimensional parameter space. But instead, let's look at the robust optimization as an example. So for example, I'm now using this robust loss here around my different training examples. And so the sum of these three here will look something like so. So this is my loss surface. And well, if I start somewhere here and do gradient descent, I will fall into this minimum, and that's it. But if I now generate multiple batches, so here I've only selected 2 out of my 3 examples. And I get here this function plus that function. And here I get this function plus that function. And the sums of them look like so. And so. So this here would be the loss surface of batch 1. And this here would be the one of batch 2. And of course, for bigger training sets, we have, infinitely, we have combinatorially many batches that we can find. And this batch, for example, is not going to be helpful to fall out of the local optimum. So if I start with my gradient descent hiker here, well, I will fall into this optimum and that's it. But if I start with my gradient descent hiker here, all right, the gradient is very flat, but still if the hiker does follow this gradient, he or she will fall into this minimum, which is the lower of the two local minima. So what you do as you change the batches is that really the way I'm thinking about it is that you have this, if I do full gradient descent, I have this static loss surface. And if you do stochastic gradient descent, this loss surface sort of starts to tremble under your feet. Yeah? It's like an extreme earthquake, which changes the relative height of minima. And then you have your hiker with the earth, moving under his or her feet, is always trying to fall into the next, or descend into the next local optimum. And empirically, and this is now a poor low-dimensional picture, but empirically we find that stochastic gradient descent gives us deeper minima. Now, if we change the batch all too quickly, it may be useful to average a little bit over time. And this can be done by introducing momentum. And moreover, it is possible to then adjust learning rates for different parameters. Who of you has looked at Adam before? Okay, a little bit. Yeah, so I think I might still talk about that a little bit next time. Very good. Let me give the briefest of summaries. It's when we say we want to optimize neural networks is this innocent looking equation. And the reason that much of the community has shied from neural networks for so long is that there are so terribly many choices in all of these things. Yeah? So architecture alone, even when we've decided on we want a feed-forward neural network, a non-spiking one, even if we say we just use this regular kind of architecture, not a sparse connectivity, there is this combinatorially large search space. And those many, many decisions, design decisions. And this has this is one of the things that has put off people for a long time. But it turns out that, given enough compute, given enough training data, and given good choices for these, neural networks are currently impossible to beat. And this is why we'll continue to discuss some of these choices, and next time in particular, how to perform this minimization, and why we will, in the weeks until Christmas, look at different forms for the neural network, including flow-based models, diffusion models, and so on, that can solve also harder problems than just classification alone. Good. With that, thank you very much. See you on Thursday.